This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome to day 2 of section 5.3, logarithmic functions. Yesterday we learned how to convert between exponential and logarithmic, and today we're going to solve by converting those into logarithmic equations. So check this out. If in example 8, if you wanted to find the log base 3 of x and that were equal to -2, it's a lot easier to solve the exponential version. So you switch them around, switch the power and the exponent, and you get 3 to the -2 is equal to x. So what is 3 to the -2? If you can figure that out, then you've got x. Remember, you've got a negative exponent. Negative exponents mean fractions, and in this case, you can take the reciprocal. It becomes 1 over 3 squared is equal to x, and x is equal to 1/9. Done. So what is the power? So bringing it back, you can ask, what is the power in base 3 that will produce an exponent of -2? If you have an exponent of -2, then the power would be 1/9. Here, log base x of 25 is equal to 2. Well, just switch them around. You've got x squared is equal to 25. And so x could equal 5, or algebraically speaking, -5. It would satisfy this equation, but it doesn't satisfy the original, because with logs, you can't have negative bases. We're just not going to try and go there. We want to only have bases that are a positive and also not equal to 1. So 5 is the answer. Example 10, you've got log base 10 of 10,000, and in order to solve this, there's no equation. If we want to evaluate it, if you evaluate expressions, there's no written equation. But in order to convert this, you've got to turn it into an equation. We introduced x, and so when they give you just an expression, just write equals x, and then you can switch it around and say 10 to the what equals 10,000? Well, 10 to the 4th. 4th is the exponent. Again, here, when they ask you to evaluate an expression, it's really difficult to evaluate an expression, especially when you're first just learning it. It's a lot easier to just write it in terms of an equation. I don't know what this is, but I'm going to say it's just equal to x. Then you switch it around, and you get 10 to the x is equal to 0.01. So what number would, when you raise 10 to that number, what exponent would equal 1 over 100? I'll give you a hint, it's negative. So I want to know who is the phos for, and in this case you can say the phos is for us, phosphorus. Bam! That's your element for today in this video. We've got log 6 of 1 is equal to x, and so and the equals x isn't written, but you can just throw it in there, and then all of a sudden it becomes something you can easily change into an exponential equation. 6 to the what power is equal to 1? Well, if you take 6 to the 0 power, that will equal 1. And you can generalize that. You can say for any base a where a is greater than 0 and a is not equal to 1, if you have any base and you take the log of any base to 1, that would equal 0, because a to the 0 equals 1. Just translating this, this is what you get. Now remember, we don't want to look at bases that are negative. We want to only look at bases that are positive, and base of 1 is going to be kind of not interesting. It would actually satisfy this equation, but bases 1 are just going to flatline on a graph. Here you can see log of base a of a. If you switch this around, the exponential version would be a to the 1 is equal to a, and so therefore you could say that log of any base of that base is equal to 1. Those are some properties you can remember. Here's our standard exponential equation, y equals 2 to the x. We've seen this quite a few times, and you can see here are all the powers. But if you wanted to, you just formally say right here what the log, what the inverse and the exponential equation are logs. A log function has powers as the input, exponents as the output, a domain of 0 to infinity, because the range over here is a 0 to infinity, a range of negative infinity to positive infinity, because the domain for the inverse, for its inverse, would be here. And then the exponential equation's intercept was the y-intercept was 0, 1, so therefore the x-intercept would be 1, 0 for the inverse here. The logarithmic equation is the inverse. The asymptote would be a horizontal asymptote of y equals 0, and a vertical asymptote in the inverse, x equals 0. If you wanted to draw those, it would look kind of like this. Remember, there's a vertical asymptote along x equals 0. We're going to intercept at 1, 0. That's the x-intercept. And so it's going to look kind of like this. As we can see here, when you take the inverse table, you get the log y equals log base 2 of x. Well, switching it around, it's actually going to be a lot easier to take to make a table out of the exponential version than it is the log, because you have the freedom here to choose easy y values and put them into the equation and then calculate the x values here. There's nothing that says you can't choose the y's. Why not? You just choose the y's, put them into the equation, and calculate out the powers. And so, as we can see, this is what it looks like again. Anyway, I'd like you to start assignment 5C2, copy the problem list, do the first problem, and I will see you in class.